Hello everyone, welcome to this video. Today we will learn about phase rule and stability criteria, and we will also look into some real life examples of the same. Have you ever wondered how ice, water and steam can all exist together perfectly balanced at a single temperature and pressure? Well, behind that fascinating balance lies one equation, the phase rule. It governs all changes in states, everything from molten lava cooling into rock to metal alloys forged in industries. So, what is phase rule? The phase rule is a thermodynamic principle that describes the relationship between the number of phases, components, and degrees of freedom in a system at equilibrium. It is given by the equation F is equals to C minus P plus 2. Here, F is the degree of freedom, C is the number of components, and P is the number of phases. This equation helps us determine the number of independent variables like temperature and pressure that must be specified to completely define the state of a system. Now let's understand what each term of the phase rule means. Firstly, we have P, which means phase. A phase is a physically distinct, homogeneous, mechanically separable part of a system. For a phase to exist, it must have uniform physical and chemical properties throughout, and it should be separated from the other phases by a clear boundary. For example, ice, which is a solid, and water, which is a liquid, and steam, which is vapor, are three different phases of the same component, H2O. And another example is, in a homogeneous NaCl solution, there is only one phase because there is no clear boundary between the NaCl and water. Next up, we have components. A component is the minimum number of chemically independent constituents required to define the composition of every phase in a system. For example, boiling water has one component since there is only one chemical component, H2O, even though there are two different phases, the liquid phase and the vapor phase. While in an NaCl solution, which is only one phase, has two components which are two different chemicals, that is NaCl and H2O. Now, finally, we are talking about degrees of freedom. The degrees of freedom are the number of independent variables such as temperature, pressure, or concentration that can be changed without altering the number of types or phases present in a system at equilibrium. Now that we're familiar with the phase rule equation, let's understand how it works. The phase rule equation tells us how flexible a system is. Now, if the phase rule F is equals to 0, the system is called invariant. That means that no variable, whether it may be temperature or pressure, can be changed. Both of them have to be fixed. A good example is the triple point of water, where the solid, liquid and vapor coexist only at a specific temperature and pressure. Next up, we have F is equals to 1. Here the system is called univariant. Here only one variable, either temperature or pressure, can be changed, and the other gets automatically fixed by the system. For example, during the boiling of water, if we fix the pressure, the temperature is automatically determined. And then we have F is equals to 2. This system is called bivariant. This means that we can independently change both temperature and pressure without disturbing the equilibrium between the phases. For example, a single phase gas or liquid system is usually bivariant because it can exist over a range of conditions. Now, let's apply the phase rule to the simplest and the most familiar system, which is water. For water, the number of components is 1, that is C is equal to 1. Let's look three different cases. Firstly, we have case 1, only liquid water. Here there is just one phase, therefore P is equals to 1. And when we calculate the equation for F, we get F is equals to 2. This means that the system is bivariant. Both temperature and pressure can be changed independently without disturbing the single liquid phase. Now let's look into case 2, liquid water in equilibrium with vapor. Here we have two phases. Therefore, when we calculate F is equals to 1, which means that the system is univariant, which means if we fix either temperature or pressure, the other gets automatically fixed. Then we have case 3, which is ice, water and vapor coexisting at equilibrium. Here all the three phases are in equilibrium. And so P is equals to 3 and F is equals to 0. This means that the system is invariant and all the conditions must be fixed. This happens only at one specific condition known as the triple point, where ice, water and vapor all coexist in perfect equilibrium. Now let's see how this triple point of water looks like. Okay, now that we have seen what the triple point of water looks like, let's dive into some of the practical applications. When it comes to practical applications of the phase rule, we usually either keep the temperature or the pressure constant. And when one of these variables is fixed, the phase rule reduces to F is equals to C minus P plus 1. This simplified version is known as the reduced phase rule. It's especially useful for condensed systems like metals, alloys and minerals, where the pressure changes are very small or negligible. So instead of dealing with both temperature and pressure, we focus on just one variable, which makes the analysis of the systems much easier. Now that we have understood the phase rule and its applications and examples, let's look into some of its limitations. It is important to remember that the Gibbs phase rule is only valid under true equilibrium conditions. It assumes that the system is at equilibrium. Only pressure, temperature and composition will affect equilibrium. No external fields like gravity or electric effects. All phases are perfectly homogeneous. Real systems may slightly deviate from these metastable states or show slow kinetics, which hinders the application of the phase rule. Now we will understand the stability criteria and how it's related to the phase rule. In thermodynamics, a system is said to be stable only when it's in equilibrium and shows no spontaneous tendency to change its state, whether it's temperature, pressure or composition. If there's a small disturbance that does occur, a stable state will resist that change and return to its original condition. Now, based on how a system responds to such disturbances, we classify that equilibrium system into three types. First, we have the stable equilibrium, where the system returns to its original state after a disturbance almost immediately. Then, we have the metastable equilibrium, wherein the system appears stable but can change if a larger disturbance occurs. And then we have an unstable equilibrium, wherein even a small disturbance can drive the system away from its state of equilibrium. These categories help us understand how systems behave and change when the conditions are changing, or whether they are remaining steady, where they are resisting change or transforming spontaneously. Now, we will look into the condition for stability, which is best understood by using the Gibbs free energy equation, which is defined as G is equals to H S T, where H is equals to enthalpy, T is equals to temperature and S is equals to entropy. At constant temperature and pressure, the equilibrium state of a system corresponds to the minimum value of Gibbs free energy. What this means is that if the Gibbs free energy decreases, the system changes spontaneously. And if the Gibbs free energy increases, the system is unstable. And when the Gibbs free energy is minimum, the system is at stable equilibrium. So, in conclusion, the phase rule gives us a powerful way to predict how many phases can coexist in an equilibrium condition under a set of given conditions. The stability criteria, on the other hand, helps us understand whether that equilibrium will actually persist if the system will change spontaneously. Both concepts are rooted in one fundamental idea, that is, a system at equilibrium has its Gibbs free energy at minimum. Together, they describe not only the possible states of matter, but also the conditions under which those states remain stable. Now, this brings us to the end of this video. Thank you everyone for listening.